An educator wants to see if there is a relationship between the number of absences for a student and the student's final grade. Use the data below to find the least squares prediction line and to answer the questions 32 to 34. So these numbers here, because I used to have these numbers in the online post, so this would have been 32, question 33, question 34. So we're going to answer these three questions at the end. Don't worry about the numbering here. The problem asks us, though, to find the least squares prediction line. In order to do that, we first have to identify which variable we're going to use as our predictor variable, or in other words, our x variable, or in other words, our independent random variable, and which variable we will let be the response variable, or the y variable, or the dependent random variable. All those mean the same thing. I think we should use absences to predict the final grade. It's not that you couldn't go the other way around. We could use final grade to predict the number of absences a student had, but I think that it's probably more useful to use the absences, the number of absences, to predict the student's final grade, because that might let us know if there is a relationship between absences and final grade, and if we see that an increased number of absences reduces the final grade, then we can warn students that it's important to be in class, and we can have some actual data to back that up. So let's use this data to figure that out. So we're going to let the absences be the x and the final grade be the y. Just to understand this data, this is a student's specific number of absences. One student had 10 absences, and his final grade ended up being 70. Another student had 12 absences, his final grade ended up being a 65. So on and so forth. That's how you read the data. All right, so the first step you want to do is to kind of work with the data and do some preliminary calculations that we're going to need for our least squares regression line. So let's go ahead and do that on this sheet of paper here. So I'll start out by creating columns. So we're going to just put the data into columns so it's easy to work with. So we'll have an x column, a y column, and then we're going to, from there, fill in some extra columns. Let's start with the x and y column. Let's put these ordered pairs together in a column format. So we're going to do 10 and 70. So we're keeping the pairs consistent, right? So it'll be 12 and 65, right? 2 and 96, 0 and 94, 8 and 75, and finally 5 and 82. All right, so there's our column of values. Now what I want to do next is I want to come up with a column called x squared. And then from there, I'm going to create the column x times y. And so this is going to be the four columns. These are going to be the four columns that we need to use to create the least squares prediction line. All right, so x squared is easy. We can do that without the help of a calculator for sure. 10 squared is 100. 12 squared is 144. We see 2 squared is 4. 0 squared is 0. 8 squared is 64. And 5 squared is 25. Now for x times y, we're just going to go straight across. So like 10 times 70 gives us 700, so on and so forth. Let's do some of those other ones in our calculator here just to make sure we don't make an error. 12 times 65. When we're done with that, we get the answer 780. Okay, then we have 2 times 96. We get 192. 0 times 94 is 0. 8 times 75, that should be 600. And then 5 times 82 should be 410, right? 410. Okay, so there are our values. The next step of the process after filling in those columns is to actually total all these columns. So add up all these numbers and get your solution. So for example, we would say, 10 plus 12 is 22. That's 24. That's 32, and 5 makes 37, right? So we get 37 for the first column, and then so on and so forth. Well, I've actually already done the values here. I've already added up these columns so that we would have those answers a little faster. So let me just put those in. That's 482, 337, 2,682. So those are the values here, those totals of each of these columns. It just takes a little bit to add them up, but basically in a calculator, if you add them up, you shouldn't make a mistake, and that should be the totals you should get. Okay, so once we have those totals for the columns, the next step of the process is to give those totals names. So I'm going to give this the name, the summation of x, because I got this number 37 by adding up the x column. I'll give this number the summation of y as its name. This will be the summation of x squared. This one will be the summation of x times y. So those are the names for the 4 different values we have on the table. Now what we have to do next is to fill in certain formulas to help us calculate our least squared regression parameter estimates. So it's a mouthful there what I just said, but I'll explain what those are again later. But what we need to do next after coming up with this step is we have to get a quantity called the summation of xx, which by definition is the following. It's the summation of x squared, so this quantity, minus the summation of x quantity squared over the number of ordered pairs or the number of x values. If you look at that, that's like the numerator of our old variance formula when we learned to do the variance back in Stats 1. Alright, so that's that formula. We can actually work that out and get the solution then for that if we wanted to at the moment. I'm not going to do this here though, I'm going to do it on another sheet of paper. Let me just write some of the other formulas down that we need. We need something called the summation of xy or SSXY. And the way that works is pretty simple. It's kind of like this. It has the same structure to it if you look at that structure. It's something squared, right? So that's x times x. Well, if we're doing xy here, it's going to be xy, right? Instead of x times x, it'll be x times y. See, xx, x squared, xy, xy. Minus, here, if you think about this, is the summation of x times the summation of x. Well, for this one, because we have xy, it'll be the summation of x times the summation of y, right? All over n, which is the number of values. Okay, so those are those 2 quantities. And then from there, we're going to take those and plug them into a special set of formulas here. The first one is going to give us an estimate for our slope. That's going to be beta 1 hat. And the estimate for the slope is pretty nice. It actually is going to use SSXY over SSXX. So once we've calculated these 2 quantities, we can get the slope directly from that. Now once we have that, we have to do the final thing, which is to get beta naught hat, which is an estimate for the y-intercept for our equation. And it's going to involve the mean for the y column minus the value we just would have calculated for beta 1 hat times the mean for the x column. And if you put those things together, you will get your 2 parameter estimates. So we're trying to estimate what the y-intercept would be and what the slope would be for the true regression equation for these 2 variables, right? To get the true linear relationship of these, we'd have to know the population values of these guys. We're estimating them with this sample data. Okay, so let's fill in these 4 formulas to finish the problem, and I'm going to use another sheet of paper for that just so you don't end up having everything squeezed in on one page. Okay, so let's go ahead and do the first one, which is the sum of squares for xx. Okay, so we're going to put the summation of x squared in there. That's 337. Minus the summation of x. That's 37. Squared over n. There are 1, 2, 3, 4, 5, 6 different values, right? 6 different values there. Okay, let's work that out and see what we come up with. So 337 minus 37 squared divided by 6. You get the answer 108.83. 108.83 repeating. Little heads up, this answer must always be positive. So the summation, or the sum of squares, pardon me, for xx can never be negative. If you get a negative answer, you've made a mistake here. The only one that can be negative is this SSXY. So of all the sum of square values that we're going to learn during this process of working with regression equations, I want you to remember that this is the one that can be negative, the one with the mixed term, the sum of squares for xy. That can be negative, but not the xx one. Later on we'll learn one called sum of squares for yy. That can't be negative either. But xy, the mixed term, it's possible for that one to be negative. Okay, so let's go ahead and work this one out then. So this one requires this quantity, summation of xy, which we see is 2,682, minus the summation of x, which is 37, times the summation of y, which is 482, all over n, which in this case is 6. Remember, n is the number of original ordered pairs we had, right? Okay, so let's work that out and see what that comes out to be. It'll be 2,682 minus 37 times 482 divided by 6. Realize we don't need any special parentheses or anything, just plug it in as you see it. And we get an answer that's negative, minus 290.333, so on and so forth. So just say 3 repeating at that point. All right, now, just a little heads up. When this guy turns out to be negative, it means our two variables have a negative linear relationship between them. What that means is that essentially, as one variable increases, the other variable decreases. So as we have a higher number of absences, we get a lower grade. So the variables move in opposite directions here. We know that as the number of absences increases, the overall grade in the class decreases. That's what the negative shows. Now, we don't know that that's a significant linear relationship, right? We're not saying that it's necessarily a significant linear relationship, but because this is negative, it means the variables seem to be related in a negative way, especially if this turns out to be a significant linear relationship. We won't know that in this problem. We're not going to be testing that, but later on we'll run a test to know if it's a significant negative linear relationship. All right, so we've got the two quantities here, SSXX and SSXY. Let's plug in for beta 1 hat. This is an estimate of our slope, right? So we're going to put the XY term, the mixed term, on top over the X term, which is 108.83, repeating. Okay, so let's take those numbers and put them in our calculator and see what the slope becomes. Okay, so we have minus 290.3 repeating divided by 108.83 repeating. And we get the answer negative 2.668. Negative 2.668. So negative 2.668. Okay, so that becomes our estimate of the slope for our regression line. And then from there, we're going to get the beta naught hat value. So before we can do that value, we have to work out the average x value, which is going to be the summation of x over n, and the average y value, which is the summation of y over n. Now, the summation of x is 37, right? We have that value here. We're going to divide it by 6, which is the n for the problem, the number of ordered pairs we had. Summation of y is 482. We're going to divide that by 6 as well. Okay, so that'll give us the average x and the average y value. Okay, so 37 divided by 6 ends up producing the answer 6.16 repeating. And then if we do 482 divided by 6, we get the answer 80.3 repeating. So we have 80.3 repeating. All right, so those are our sample x bar values and y bar values, right? So x bar and y bar are the average x value in my list, the average y value in our list. Now we need those because you see in the formula for beta naught, this formula here, we see that we have y bar minus beta 1 hat times x bar. So we have to put in those averages into our formula now. Okay, so let's put the y bar, which was 80.3 repeating, minus the estimate for the slope, which is minus 2.668, times the x bar value of 6.16 repeating. Okay. So let's plug that in and see what we get. So we'll have 80.3 repeating. Minus and a minus here will become a plus. So I'll have plus 2.668 times 6.16 repeating. Hit enter and we get the answer 96.786. 96.786. 96.786. All right, so once you have that value, what you have to do is plug it into your regression equation. So we're going to have the y hat is equal to. Now the regression equation that we're going to use is this format. It's the beta naught hat plus beta 1 hat times an x variable. So the y hat stays there as a variable. Beta naught we see was 96.786 plus the slope, which we calculated as negative 2.668 times x. Of course, you can drop the plus minus and just say minus here. So 96.786 minus 2.668x is the solution. All right, now once you have that, your basic answer to the first part of the question is done. You've calculated the regression line. We have that. Now we want to go and answer the 3 questions that were listed after that to kind of interpret this line. Okay, so let's go back to those questions and do the solutions for those as well. Okay, so I've gone ahead and recorded our equation down here, the one we came up with, and I've gone ahead and labeled our variables as we use them in the equation. So remember, x here represents the number of absences going into the equation, and y is the final grade that's predicted for student, or for, sorry, the average final grade that's predicted for students who have that many absences, right? So for example, if I entered 7 in for x, this y value is the average grade that you expect for students who have 7 absences. Okay, so when I read these questions, we'll be able to use this equation to answer it then. So based on this line, what would the average grade be for a student who missed 6 days of class? Well, let's go ahead and just plug 6 right into our equation real quick, right? So let's see what that gives us. So we're just going to plug it in just as you see it here. We're going to have 96.786 minus 2.668 times 7, or times 6, pardon me. And when you do that, you get the answer 80.778. 80.778. So the answer for the first question here is 80.778. All right, for the next question, they ask, what does x equals 0 represent? Well, of course, first of all, it represents the y-intercept, right? The y-intercept. So that much we know for sure, that it represents the place where the line intersects the y-axis. But more importantly, for the practical real-world interpretation, it represents, no absences for a student, right? So it represents 0 absences, or no absences. Okay, 0 absences. So basically, perfect attendance, right? All right, and then it says, what average grade does the model predict for students who have perfect attendance? So for students who have perfect attendance, they want to know what's the average grade. Well, what we do is we simply enter 0 in for x. And if you put 0 in for x, it's going to cancel this term out completely, and you'll be left with just this term, which turns out to be, of course, 96.786%, right? So it says, on average, students with perfect attendance will have about a 97% average, according to this model. Okay, so that's it. And of course, these 3 questions help us understand how this equation is used and how to interpret certain parts of it. A little mention about this x equals 0 quantity. You can't always interpret that in every model. In some models, that quantity is nonsense. But here it makes perfect sense because x is the number of absences. It'll be 0 absences for this group. So here the x makes perfect sense and it's easy to interpret as a result.